I think you don't have. A very good afternoon to all of you. Thank you all for coming to my talk. And first of all, I would like to thank the organizer, Ideta Sensei, for giving me the opportunity to present my work here. So today I'll be discussing about work which I did previously before joining HiSol. This work is related to a new family of materials, which is basically called Kagome metals, but these are slightly distorted. So the title of today's talk is Mapping the Rich Electronic Landscape of Distorted Kagome Metals. So before I move into the details of the talk, I would like to give a brief introduction about the technique that I use. The technique is called angle-resolved photoemission spectroscopy, or in short, ARPES. And it's basically based on the principle of photoelectric effect, for which Einstein explained it and got the Nobel Prize in 1905. So the principle is based on two basic conservation, the energy conservation and the momentum conservation. So what basically happens is you have a crystal and you shine light on the material. The light can be of any energy from VUV to soft X-ray, but the energy should be greater than the work function of the material, which usually is around 4 to 5 eV. And if the energy of the light is greater than the work function of the material, the electrons gets ejected out of the material. We can measure the kinetic energy as well as the angle at which the electrons come out. Then we can do some back calculations and we can actually measure the binding energy of the electron inside the solid, as well as the momentum, which basically is your wave vector. So we can plot your momentum and binding energy along the in-plane directions, and you get the Fermi-surface. Or if you take the cuts at higher binding energies, as you can see in this movie, then you can also get the information about the constant energy contours at high binding energies. So basically you can get a 3D map. You can map the in-plane momenta as well as the out-of-plane momenta. This is slightly complicated in the sense that your in-plane momenta are conserved in the crystal, but the out-of-plane is truncated, so it's not conserved. But we can use an inner potential and then also calculate the kg. So basically you can calculate kx, ky, and kg. So you can get 3D information about the electronic structure of the material. So if you take a cut at the top, which is called the Fermi surface, and if you take a cut at increasing binding energies, then you can also take the constant energy contour and you can explain the size and the nature of the pockets. So this will be handy when we discuss about the materials. And I know there are some people who are already an expert in ARPES, but maybe some people are not in the ARPES field. So I would like to explain all of these things so that the rest of the talk will be better clear. The other thing that we need to know is, so if you have an ARPES spectra as shown here, you can take a cut either along this. So basically you fix the energy and integrate along the momentum directions, called the momentum distribution curve, or MDCs in short. You can also take a cut along the energy direction, that is you fix the momentum and scan the energy, and then you can get the energy distribution curve, so or the EDC. So this we will be using frequently in ARPES. And what exactly is being measured in ARPES? So ARPES, the spectra that you have seen just now, is a convolution of so many factors. We have the photoemission matrix element Fx, which comes from your transition matrix element. So it depends on the photon energy, the polarization of light, as well as the crystal in which it's aligned. You also have the information about the spectral function, where you also have the information about the many body functions, which usually DFT does not give. And you can do more detailed analysis from the band position or the line width, and can also get into information about the electron phonon or electron magnon interactions, basically many body interactions. Apart from that, you can get information for only the occupied states, at least in ARPES. And your resolution is also included there. Resolution of the detector, the light, as well as the lifetime of the electrons. All of these plays an important role in the ARPES spectra. So with this brief introduction about ARPES, let's move into the details of today's talk. So basically, my talk will be focusing on Kagome lattice, and I'll try to convince you why these are very important. So we all know about the flat bands in various lattices. Like one of the most important example is samarium hexaboride, where if you look at the electronic band structure, you have flat bands lying near the Fermi level. Samarium hexaboride is a very peculiar case and a very interesting case. So here, samarium exists in mixed valence state, both +2 and +3, and the samarium 2+ states have flat bands very near to the Fermi energy. So what it does is this samarium 4F actually forms a condo singlet with the conduction electrons, and it plays a very important role in the resistivity because at high temperature it's a bad metal, but at low temperature the resistivity increases, and people have predicted that at low temperature where the resistivity saturates, it also hosts exotic topological surface states. So the flat 4F bands plays a very important role in the exotic physics in the system. Apart from that, cerium antimonide also shows condo physics, where you also have 4F flat bands lying near the Fermi level. So these are some examples where you have flat bands from the electronic structure of the samarium itself. So you have samarium 4F. So you will have flat bands in its electronic band structure. Apart from that, there have been a plethora of studies on these kind of materials where these are not correlated in the sense you do not have this kind of 4F flat bands. But even in these non-correlated materials, if you try to stack these materials on top of each other at certain angles called the magic angles, then these materials also shows exotic physics like superconductivity. And people have found from ARPES that there are flat bands lying near the Fermi level. So you can see these flat bands play a very important role in various electronic properties of material, and one can design flat bands by either these methods, which is slightly more tedious, and in these cases the materials are not homogeneous also, these are slightly difficult, or you can also have these kind of materials where you have flat bands from the 4F states itself. However, recently there have been a lot of studies on materials called Kagome lattices, where here also flat bands can be observed in the electronic band structure. But in this case, it's not because of 4F states like samarium 4F, cerium 4F, or stacking of these layers. But in this case, the flat bands arises from the structure, the geometry of the lattice itself. So this is a Japanese basket where you have these triangle-like features and they connect at the corners. So you have a hexagon in the center. And these kind of structures are possible in real materials also. So basically a Kagome lattice is a two-dimensional network of corner-sharing triangles. And then because of the geometry of the lattice, you can have flat bands in its electronic band structure. So if you write a simple s-orbital tight binding model, then you can actually find flat band. But interestingly, not only the flat bands, you can also have Dirac cones in its electronic band structure, and then you can also have band of singularities. So you can see that now we can actually discuss about various interesting properties of a material just from this lattice itself. And this is not just based in predictions, but there are many reports where people have found flat bands lying near the Fermi level, as well as Dirac cones for a transition metal Kagome lattice, FeSN. There have been other studies where Fe is replaced by cobalt, which is also Kagome material. And there also you have flat bands and Dirac cones in its electronic band structure. This is not limited to just these flat bands and Dirac cone, but even this material CO3SN2S2 is predicted and also experimentally realized to be a Weil semi-metal, where you can see this Weil cone from soft X-ray ARPES studies, and you can also see these Fermi arcs in its electronic band structure. And also you can have two Dirac cones lying in the same K point for Fe3SN2. So those were the initial studies on binary Kagome metals, but there have been other materials like 166 family of Kagome materials, which are famously known as 166, where you can replace this rare earth with various other rare earth elements. And these Kagome is formed by the manganese atoms. So this is one study by Hassan's group where this is the ARPES study where they see hole-like bands at the K point, and using STM and DFT calculations, they were able to find a gap at the Dirac point, which extends up to the Fermi level, and the gap is around 170 MeV above the Fermi level. And we also did similar works on other family of materials like HOMN6SN6 and ERMN6SN6, where we found Dirac-like states at the K point. And we also did some work on these breathing Kagome lattices, where you do not have just one flat band, but multiple flat bands. Here, the bands are slightly broad because the measurements were performed at around 270 Kelvin, because this is a semiconductor and there is a lot of charging at low temperatures. But you can at least see there are multiple flat bands in this electronic band structure. And the other family, which is really interesting and has attracted a lot of studies, is this Kagome AV3HB5, where you have three elements in this family, where A side can be replaced by potassium, rubidium, and cesium. And in all of these materials, they found charge density wave as well as superconductivity at low temperatures. So these were one of the initial materials where people were really, really interested. And there are a lot of studies on this. But one thing that I would like to state here that though there are many reports supporting it and against it, but in general, people think that the van of singularities plays a very important role in the exotic physics in the system. So you have multiple van of singularities near the Fermi level, and the nesting vector plays a very important role to support the charge density wave in the system. And then similarly, you can have other Kagome materials when you replace vanadium by titanium. So the vanadium is the material which forms the Kagome lattice. So I think I have explained different families of materials where one can actually have interesting physics in the system. Today, the talk will be on a new family of Kagome materials called LnTi₃Bi₄, and I'll start with ytterbium, which is also a Kagome where you have the structure shown here. So these zigzag chains are the ytterbium atoms, and this red atoms are the one formed by titanium, and this is the bismuth, the green one. So if you look closely along this direction, these titanium atoms are not in the same plane, so it's slightly distorted, and you can see it more clearly in this direction. These are the zigzag chains of ytterbium atoms, and the Kagome lattice is seen clearly from this picture. The structure is orthorhombic, where the c-axis is huge. So one important advantage for ARPES measurements at least is you have to cleave the samples. And if the cleaving is not good, then you will not get good data. But in this case, the samples are very easily cleaved. So you can take out layer by layer actually. But the only problem with the samples is that these gets oxidized very easily. So we did all the experiments by making the samples in a globe box. And then as soon as the samples were prepared, we inserted the samples in the road lock. So the DFT calculation as shown here shows there are multiple van of singularities in its electronic band structure, as indicated by this 1, 2, and 3 purple arrows, as well as flat bands. This is the one without the inclusion of spin-orbit coupling, and these calculations are with the inclusion of spin-orbit coupling. There's not a huge change, but if you look here around the X point, you see a Dirac cone, and with the inclusion of spin-orbit coupling, it seems to open a gap. And this is the Billon zone. So this will be handy when we discuss the Fermi-surface. So we will be mostly interested in this gamma Y direction, which is the gamma M, and the gamma A direction, which is the gamma K direction. And these are just the transport measurements where till the lowest temperature also, we could not find any signs of magnetic transition. So this material is non-magnetic. So we started with the ARPES measurements, basically the Fermi surface. All the measurements are done at 15 Kelvin. So if you look here, there is a circular pocket at gamma, and then you have a hexagonal pocket along gamma M or gamma K, and you also have additional pockets around the K point where you have a circular pocket and a triangular pocket. So the ARPES features can be seen clearly. And then we did DFT calculations in collaboration, and even though it looks complicated because you also have surface and bulk together, in general, the agreement is okay because ytterbium has 4f states and DFT doesn't work well with 4f states. So in our calculations, ytterbium 4f states are frozen. So we have used a high value of U to keep the 4f states away from the Fermi level. These are the constant energy contours I discussed previously. So you can take a cut at different binding energies. So when we move to higher binding energy, what we see is this pocket size decreases, whereas the pocket at K increases. What it indicates is that these are electron pockets, because if you have an electron pocket and you take a cut at different binding energies, its size will decrease. But if you have a whole pocket and if you take a cut around different binding energies, its size will increase. So from here, we can at least say, okay, the nature of these pockets are different. And we took a cut along gamma M direction. So this is the first Brillouin zone, and this is the higher order Brillouin zones. So in the first Brillouin zone, the intensity is not good, whereas at higher Brillouin zone, the intensity is slightly better. And this is due to photoemission matrix element effects I discussed earlier. We change the photon energy again, and this is slightly better, where we see that in fact there are two bands. This may not be very easily visible here, but if you take a cut along this direction, zoom it, take a cut along this direction, then you can easily see two bands denoted as alpha and beta. And we've taken an MDC along this direction and then fitted using two Lorentzian and Gaussian peaks, which indicate there are two bands. The DFT calculations also support this, because in DFT you see there are two bands alpha and beta, which shows slightly cagey dispersion because these are bulk bands. And then you also have this gamma band from our experiment. So the DFT calculations are in very good agreement. However, you see a very clear sharp band here, delta, which is not there in our DFT calculations. So we did surface included calculations where these bands is also reproduced. So these are surface bands. So the next thing we wanted to take is we wanted to take a cut along different directions. So these directions are perpendicular to each other. You see the direction is from gamma to M and then M to K to gamma. So basically when you take this cut, what you see here is there is a saddle point here. So these are the Vann singularities. So in fact, there are two Vann singularities in this electronic band structure around 150 MeV below the Fermi level. Apart from that, you see multiple flat bands, in fact, 4 in this electronic band structure. Our DFT calculations also show that there are two flat bands and Vann singularities. The DFT calculations has been shifted by around 200 MeV to match the ARPES, but you only see two flat bands here in DFT, whereas in experiments you see 4. And the reason may be because we did not include ytterbium-4f in our calculations. The orbital resolved DFT calculations suggest that these flat bands originate from titanium D, mostly titanium dx square minus y square and titanium dxy. So you can see that these flat bands are originating from titanium D, which basically forms the Kagome lattice. So the next thing was that we wanted to do a photon energy dependence. So we aligned our sample along gamma K, MK gamma. This is the data with 55 EV. And you see Dirac-like state along K and then multiple flat bands. We have taken an EDC along this direction and then integrated it, which also clearly shows there are 4 flat bands. And then we did the measurements by changing the photon energy from 40 to 60 EV, normalized it and plotted on top of each other. When we look closely, what we see is that these two flat bands show a slight dispersion, whereas these do not. Similar is the case for this. This is the data for K gamma K direction. What we did is we aligned the sample along K gamma K and did the similar measurements and integrated it and normalized it and plotted on top of each other. In this case also you see these two flat bands dispersing, whereas the two at higher binding energies does not disperse much. So we wanted to understand these in more detail. So what we did is we have aligned our sample along this direction and changed the photon energy. So basically in this case we did on resonance measurement. So what we did is we know the binding energy difference between ytterbium-4d and 4f. So we can change our photon energy, basically tune it so that there is more excitation from the ytterbium-4f. So there are two photon emission going on here, the normal one as well as the ytterbium-4d to 4f transition and then photon emission. So in this case, you have this 4f emission very strong. So from here, we can say that these are ytterbium-4f flat bands, whereas the one near the Fermi level were from the titanium D states. And you know that titanium D states are not very correlated, because if you look at the electronic structure, these are slightly dispersive. But in this case, you see that these are very non-dispersive. So this is very interesting because this is coming from the lattice itself, because it forms the Kagome lattice. The other thing is we wanted to look at the K points. So I discussed previously that the Kagome lattice hosts Vann singularity, flat bands and Dirac points. We already have discussed about the van of singularities and the flat bands. The next is the Dirac point, Dirac cone. So if you look at this K gamma K ARPES plot, we change the energy and then we again look at this K gamma K direction. What we see is that the ARPES intensity is slightly better in this case. So we are just focusing on this one. We see a Dirac-like state here where the Dirac cone seems to be slightly above the Fermi level. Our DFT calculations, even though it doesn't match in the binding energy range due to the limitations of DFT, it shows a Dirac-like state here, which also originates from titanium D states, specifically titanium dx square minus y square. So we have taken the K gamma K ARPES plots as a function of photon energy from 40 to 60 eV. And apart from the photon emission matrix element Fx, you still see these Dirac-like states at the K point. So what we did is we take an MDC, basically fix the binding energy and integrate it along the direction, this cut. And we have these MDCs for various photon energies. What we can do is next, we can fit these using this Lorentzian Gaussian functions. And when we track these points, what we can find out is that these K points are dispersive. The bands at the K point are dispersive. This suggests that the band at the K point is a bulk band. So I would like to conclude here in the first part stating that I discussed that a material which has a Kagome lattice can host van of singularities, and we found van of singularities in this material. I also discussed that it also hosts flat bands. So the first two flat bands are from titanium D states, we could resolve it. And the second two flat bands are from ytterbium-4f states. We also found out that there is a Dirac cone at the K point. And these are from the resonant photon emission where we could resolve these 4f flat bands at higher binding energies from ytterbium and the one near to the Fermi level from titanium. And our DFT calculations are more or less in agreement. You don't see those higher binding energy flat band because the ytterbium-4f states are frozen in the core. However, what we missed in this study was that the material is orthorhombic, but I discussed the Billon zone in a hexagonal, using a hexagonal Billon zone. Though strictly it's not hexagonal, we call it pseudo-hexagonal because the distortion is very small. But we were thinking of what will happen with distortion, which we could not do in the previous study. But in this case, you have lanthanum replacing ytterbium. This is also non-magnetic. Everything is same. The structure is also the same. There is a slight difference in the bond length because of distortion. And let's see what happens when there is a distortion in this lattice itself. And this is quite different from these Av3Hb5 materials because there you have only 3 elements, but here you can replace the rare earth side with different elements. So it gives a lot of flexibility. This is the Billon zone for this material. And if you look closely, you can see that there is a hexagon here, and oppositely again there is another hexagon. So these are the points which are related by symmetry, but other points are different. So we have named this as M bar, but opposite to this, you can see there are other M points, but these are not M bar, these are M prime point because it's not related by symmetry, because there is a C2 symmetry here and not C6 symmetry. The other thing is you also have these K prime points, and similarly, you have these K points. So the next thing is to understand the importance and the significance of these distortions in the electronic band structure. So for that, again, we start with the Fermi-surface measurement. The Fermi-surface measurement is in good approximation with our DFT results. If you look closely here, it's slightly rotated compared to DFT. This pocket is slightly elongated, and this elongated direction is the gamma M direction as shown from the DFT. So we can pinpoint the gamma M direction as well as the gamma M prime direction. So that's the first thing we have to do. So once we understand the direction, whether it's gamma M or gamma M prime, then we can take a cut along that direction and see how the band structure changes. So this is the band structure from DFT. And here, interestingly, what we find is that we have a band of singularity around the Fermi level. So apart from that, you also have other band of singularities as well as flat bands, two flat bands. And these flat bands are slightly dispersive. So as I discussed before in Kagome lattice, you should have a flat band which is perfect. But in this case, you see that it's not perfect, it's slightly dispersive. And I can come to the reason like why is slightly dispersive. So now we have already pinpointed the directions of high symmetry point. And here we take a cut along gamma m, k prime gamma. We can again take a cut along gamma m prime, k prime gamma. You just rotate the Fermi surface and take different cuts. And as soon as you take a cut, you see a stark difference in the electronic band structure. Along gamma m, you don't see a band of singularity near the Fermi level, whereas along gamma m prime, you see a band of singularity near the Fermi level. The flat bands are still intact along both the directions. Uh, Even the second band of singularity changes its binding energy. So you can see there is a strong anisotropy in the electronic band structure, and this anisotropy comes itself from the crystal distortion. I have already discussed this one, but let's see what happens at the K point. If you look at the K point, which also has K bar and K prime because of the breaking of the C6 symmetry, you can see these bands which are a Dirac-like state does not have a Dirac point at the Fermi level. So if you extend it, it will be slightly above the Fermi level. Whereas in this case, you have a Dirac point exactly at the Fermi level. You can see this better if you zoom it and you can track these bands, or you can also take a second order derivative where you see these features being more clear, or you can take an MDCs. So basically from all of these, what you see is that even the Dirac cone has shifted. So in one direction, the Dirac cone is at the Fermi level, whereas in the other is not. So now the question there may also be some questions like, okay, the photo emission matrix element may play a very important role because you are changing the direction, you are rotating it. But however, that is not the case for LnTi₃Bi₄, because from DFT calculations, you can see if you take a cut along gamma m prime or gamma m, you see it actually is in close agreement with our experiments, because in gamma m prime, you have a band of singularity near the Fermi level, whereas along gamma m, you do not have a band of singularity. You also have a slight change in the dispersion of the flat bands. Though it's slightly more difficult to track this in experiments because the flat band intensity is not very great, but at least we could see these changes very easily. We can further see it from DFT and see the orbital resolved DFT calculations. So all of these fat bands, what you can see here is the contribution from these particular orbitals. So this is the high symmetry point again. So you see x gamma x basically represent your k gamma k direction. So at k gamma k, you have a Dirac cone slightly above the Fermi level. And this Dirac cone also comes from these titanium d orbitals. And similarly along a gamma a, which is your k prime gamma k prime direction, the Dirac cone is exactly at the Fermi level. So DFT also shows that it's not an artifact of experiments or photoemission matrix element effects. Again, along y gamma y and y prime gamma y prime. So y gamma y is your m gamma m, and y prime gamma y prime is your m prime gamma m prime. So basically along one direction, you don't see a van of singularity around here. But along the other direction, you see a van of singularity. And again, these van of singularities come from titanium d orbitals, which you can basically see from these calculations also. So if you look at the states near the Fermi level, all of these states have contribution majorly from titanium d orbitals. So from these studies, what we can conclude is that you have the electronic band structure mostly dominated by these titanium d orbitals. And if you recall, the titanium d orbitals or the titanium atoms forms the Kagome lattice. So you can see that the band structure or the electronic structure near the Fermi level is mostly dominated by the Kagome lattice. Though there is a spaghetti of bands, it's not like a simple s orbital tight binding model, but the major features or the Dirac cones or the band of singularities or the flat bands mostly come from titanium d orbitals. And the other interesting thing is that even the anisotropy of the crystal plays a very important role. So in this case, all the cases that we discussed, we can see that there is an inherent anisotropy in the electronic structure, and it comes from the structure itself, the Kagome lattice structure. So then finally, I'll discuss briefly about the next topic, which is cerium titanium bismuth. And this is slightly interesting. However, we were the one who did ARPES and the other group did neutron diffraction measurements. So as I already discussed, I wanted to stress on the fact that this family of materials are slightly interesting than the other 135, even though these do not have charge density waivers or superconductivity. And the reason is, you see here, you can actually replace the A site with a large number of lanthanide elements. You can replace by lanthanum and ytterbium, which we already discussed, both are non-magnetic. But then if you replace by europium, it becomes ferromagnetic. And then if you replace by some gadolinium, it becomes antiferromagnet. So you can change your A site element and you can tune the magnetism of the system from non-magnetic to ferromagnetic to antiferromagnetic. Lanthanides smaller than terbium were not possible. If you dope cerium with terbium, then you can have a mixed phase, which they have predicted it to be Suri-Kagome family. And you can also prepare from terbium to lutetium, but it will not synthesize in this ARTi₃Bi₄ crystal structure. So let's discuss about cerium. Cerium has an antiferromagnetic transition at 3 Kelvin, and then our collaborator who led this study, they did neutron diffraction measurements on these material, and they found there is a spin density wave, both commensurate and incommensurate, existing in the system. They obtained from neutron diffraction. So our job was to perform ARPES experiments and see whether our ARPES measurements also indicate or at least verify the results or not. So this is the ARPES measurement for cerium titanium bismuth. These samples are easily cleavable, and you can see the data is also very good. So you have these elongated pocket, which indicates this is gamma M direction. So we can easily identify the high symmetry points. And once you identify the high symmetry points, it's easy because you can take a cut along either this direction or the gamma M prime direction. And anyway, if you just take a glance here, you can see you have high intensity points around these points, whereas you do not have those same along the other points. And you can take a constant energy contour at different binding energies again, and you can track the size of these pockets, where these size of the pocket decreases, which are basically electron pockets, and these are the hole pockets. So let's start with the DFT results. This is not specifically for cerium titanium bismuth. This is for lanthanum titanium bismuth. And this is just an approximation because cerium has 4f states. So working with cerium is slightly difficult and complicated. And if you do not have 4f states near the Fermi level, then why take so much of pain? So the idea was, let's start with a simple system of lanthanum titanium bismuth and see what happens near the Fermi level. So if you see the results, you see along gamma M prime direction, there is also a van of singularity here, even though it's not exactly cerium titanium bismuth. But the other thing is, you also see a strong anisotropy, as I discussed previously, along gamma M and gamma M prime. If you look here, the band structure is totally different. You have a van of singularity in one direction, but not in the other direction. And this is the ARPES plot in the within a very small energy range. This is along gamma M prime gamma, where you see the van of singularity. So you see here, the intensity is very high along these regions, indicated by these triangles. So these are the van of singularities along this direction. So if you take a cut along gamma M K gamma, you will find a hole pocket and electron pocket, as discussed previously. But in this case, you can see this feature here, which is very intense. You can fit it using this simple equation, and you can find that it fits good. So this is the van of singularity here. This is the Fermi-surface. According to neutron diffraction experiments, they found a nesting vector of around 0.61 and 0.57 angstrom inverse. And the lattice constant of cerium titanium bismuth is A is around 5.9 and B is around 10, around 10 point something here. So according to the neutron diffraction, they measured this QCs along the B axis, so along gamma Y. So we measured it along this, and you see there is a nesting vector along this direction. We calculated, and then we found from our ARPES measurement that this nesting vector is actually very close to this 0.61 angstrom inverse. However, you see the intensity is quite broad. It extends to a long region. So There can be other directions also where you have this nesting vector. It may be slightly shorter, and you can have both coexisting. So this we cannot say conclusively because the experiments were performed at 15 Kelvin in the paramagnetic phase, and the spin density wave is around 3 Kelvin. And it's quite difficult to reach those temperatures from ARPES. But at least we find signatures that the nesting vector is in close agreement with the neutron diffraction results. And these are the M prime points where you see the Van Hoff singularity. Along M, you do not see it. So these nesting vectors seems to match with the neutron diffraction results, and we claim that the Van Hoff singularities plays a very important role in stabilizing the spin density wave phase in the system, because if you have a Van Hoff singularity, you have a large number of electrons in that particular region. So even if you have weak interactions, it's enhanced because of these Van Hoff singularities. This is the ARPES plot, and we have overlapped our DFT results. More or less it's matching, but you do not see these alpha bands in our DFT. So we try to find the origin of these pockets, and what we see is that we take a ARPES map by changing the photon energy, again take an MDC and put it on top of each other. We see that these alpha pockets do not change with the change of photon energy, which usually signifies it's a two-dimensional pocket or a surface pocket. So since it's not there in the DFT calculations also, we assume it's a two-dimensional pocket. Further proof can be seen here, because if you take along this direction, people may say, or even the referees may thought maybe this is the band which is here, and maybe there is a difference in the DFT and ARPES, so you're not observing this. But if you look along this direction, which basically is along kg, then you see there is a huge change in the band dispersion. So these are not the same bands. So from here we conclude, okay, these are alpha pockets, and this Van Hoff singularities along the M prime, basically there are 4 M prime points. So there is a nesting along this direction, and then it matches with the neutron diffraction measurement. So basically you can have a coexisting commensurate and an incommensurate nesting vector in this case. So with all of these studies on 1, 3, 4, I would like to conclude today's talk. And what are the conclusions from here? So basically, we present a new family of materials called the LnTi₃Bi₄. These are the distorted Kagome lattices. And here we present this as a new family of materials where one can do a lot of different kinds of studies, because we can easily replace lanthanum, the lanthanide element, with cerium, praseodymium, neodymium, and so on and so forth, up to terbium. We can even try to dope these materials, and if we can dope these materials, we can try to bring the Van Hoff singularities or the flat bands near the Fermi level, and then we can see whether there is an exotic physics appearing in the system or not. The other thing is these materials are very easily cleavable, so you can cleave these materials even with a tweezer. So there may be many groups who are working on two-dimensional materials like thin films, or maybe they cleave the materials and put it on top of another material. So these materials will be very handy because you can easily cleave it. The only problem is it gets oxidized, so one has to work inside a globe box. So yeah, one can try to cleave it and see if to cleave down to few monolayers and see if there is some phenomena which can be discovered in these systems. Not much work is done on these systems. And I already discussed about this, so we can easily tune the chemical potential by either hole doping and bringing it to flat bands, or the Van Hoff singularities. So the ARPES experiments were performed at ALS beamline 10.0.1.1 and 4.03 at the Advanced Light Source Berkeley National Laboratory. Further experiments were needed, and we performed those at the Stanford Synchrotron Light Source beamline 5.2. So during the experiments, the beamline scientists were there to help us. So I would like to acknowledge Dr. Songkwan Mo, Dr. Denlinger, Dr. Don Goi Lui, and Makoto Hashimoto for the beamline assistance. The work was done during my postdoc. So I was working in the Muri grant. So I would like to acknowledge AFOSR Muri grant and the NSF Career Award. I would like to acknowledge our collaborators, Professor Arun Bansil, who helped us with DFT calculations, Dr. Ortiz, who actually discovered this AV3HB5 materials, send us the LnTi₃Bi₄ materials. So he actually sent us a lot of materials, and some of the works are still going on. And I would also like to thank Professor Manders for helping us during the experiments. And thank you for your kind attention.